Hello and good day, everyone. So we're now down to the second to the last chapter of this course, which is the design of experiment or DOE, which focused on single factor experiment. Okay, so this chapter we will discuss two basic experimental design for single factor and how to analyze or how to interpret the data out of this design of experiment. Okay, so let's start. Okay, so before anything else, before we proceed to the details of the design of experiment, we will have this first this terminology here, which is we will use this for the entire chapter and including to the next chapter. So first terminology is the factor, or we also call this as the independent variable. Okay, so it is an experimental variable which controlled or manipulated in the experiment. Okay, so it's easy to understand what is independent variable. And the second one is the response or the dependent variable, the variable used to measure the effect of the factor. Okay, so the next one is treatment, particular level of a factor in a single factor experiment or a combination of levels of two or more factors in a multi-factor experiment. So since we're talking about single factor for this chapter, so treatment is just the level of a factor. Let's say we have a factor of speed. Okay, so treatment is the level of speed. So let's say 100, 200, and 500 and so on. So that's a treatment. The next one is the experimental unit or entity that receive a particular treatment. Okay, so if we go to the multi-factor, treatment is the combination man. So experimental unit is the entity that received this particular treatment. Then sampling unit or entity where measurements are taken. So for example, if we have experimental unit of 10 still bars, then the sampling unit is two randomly selected still bars to determine the tensile strength. So out of the overall is the experimental unit. Then if we want to measure the tensile strength, for example, sa atong we have 10 still bars, then we randomly pick 2 to measure the tensile strength. Then the 2 is called the sampling unit. Okay, next one is the replication. So replication is the repetition in the application of treatment to another experimental unit. Repetition of a portion of the experiment or the entire experiment under two or more different conditions. So replication is the repetition of the treatment. So treatment man is being replicated or twice, thrice, or depending sa imuha kung giyon sa nimo pag siya pagset. Test run is a single application of the treatment for which an observation of the response is made. Okay, then the last one is the experimental design. So it is a plan, an actual procedure of the conducting experiment. So every experiment class, depending on the study, follows a different experimental design. So for this chapter, we will focus two experimental design, which is the complete block design. And there's a complete block design, there are two, the CRD and the RCBD. Okay, so we will discuss that later on. So experimental design includes the specification of the treatment, the experimental units, replication or test run, then the manner of assigning the treatment to the experimental units, and sequencing of the test run. So this is the specification of experimental design. Okay, so what is the basic requirement for experimental design? First is the replication. So it requires that each treatment must be applied to at least two experimental unit or test run. Okay, so we need to replicate in order to find the significant difference between each treatment. So we need to one. So there are also some of experimental design that what do you call that, define the efficiency of this replication. So based na sa atong i-discuss na to for this chapter, the CRD and the RCBD, which is the CRD, dili nato siya i-calculate ang replication efficiency, but in the RCBD we will calculate the efficiency of this replication. Okay, then the next one is the randomization. So allocation of the treatments to the experimental unit so that no treatment is consistently favored or disadvantaged. So to eliminate bias during sa experimentation, we conduct this randomization. So this randomization, especially if you're doing a field study, so randomization is important, especially if you're doing researches that nasa field. Let's say, for example, nakigitanom or something like one. Or even you're doing research sa kanang mga processes. So randomization is very important. So to eliminate this bias nga ma-favored siya or naay treatment nga murag mo ay nagbalik-balik ba karon, mo ay murag napaboran karon sa imong experimental design. So necessary in order that experimental error follows some probability distribution used in the model. So again, probability distribution, it was being discussed by the previous instructors. What is this probability distribution? That most of the experiment must follow this normal distribution. Then the next one is the error control. So control of known sources of variation under that treatment investigated can be achieved by the proper choice of the experimental units and uniformly in the conduct of the experiment. Then an increase in the number of replication generally improves the precision to or minimize experimental error. So this is the method to control error. So it's really important to control this error, no? Because if you're doing an experiment, especially kung naka sa field, error is always gid siya naa. So for laboratory experiment, dali lang siya i-control, but for a field experiment, bro, siya quite difficult. Okay, so let's start with introduction of what is DOE. So DOE, or the design of experiment, is a systematic method to determine the relationship between factors affecting process and the output of that process. It is used to find the cause and effect relationship. Okay, so design of experiment is a method. So if you're trying to study what would be the effect of this response to the set of the independent variable, you need to come up with a design of experiment. So you will follow a systematic method in order to find what is the cause and effect of this relationship. What is the relationship between these factors and the response or the dependent variable. Okay, so DOE has three essential components. These are, first is to estimate the error. The next one is to control the error. Then the last one is the proper interpretation of the result. So estimate the error. So estimate the error between treatment, then control this error. Then after that, if you have the result, then proper interpretation of this result. So this is the essential component of a design of an experiment. So experiments in which only single factor varies while all other are kept constant are called single factor experiments. So let's say that you want to find the cause and effect for the yield. So let's just like our previous examples regression model, that we have the yield and we have the factor of the number of height of the height of the plant and the number of tillers. So there are two factors there. So if you hold one factor constant, let's say that I will not use the plant height, but instead I will just only use the number of tillers. So just like that. So but that you cannot apply that to number of tillers is not so let's say fertilizer na lang, fertilizer. So we control the amount of fertilizer. So the yield and the amount of fertilizer is, we can use a single factor experiment. So in such experiment, the treatment consists solely of the different levels of single variable factors. Let's say for the amount of fertilizer, ang level niya is, let's say that you set the kilogram or the weight. So 5 kilograms, 10 kilograms, and 15 kilograms this is the level of the your factor. Okay, so there are two groups experimental designs that are applicable for single factor. We have the complete block design used for a small number of treatments. Then we have the incomplete block design used for large number of treatments. Since we have limited time here, since this is the last this is the last topic, so we will only focus with the complete block design, which is commonly used for a small number of treatments. So under the complete block design, there are two. Actually, there are three, but I will focus only for the two which is commonly used in doing an experiment for a single factor experiment. So first is the completely randomized design, which is also called as the CRD. And the second one is the randomized complete block design, or the RCBD. So for this video, I will only discuss what is completely randomized design, or the CRD. Okay? So what is completely randomized design? So a CRD is one where the treatments are assigned completely at random, so that each experimental unit has the same chance of receiving any one treatment. Okay? Then any difference among experimental units receiving the same treatment is considered as the experimental error. So anything. So if you have a treatment in any experimental unit versus, let's say your experimental unit is the plot. So every experimental unit will receive equally the chance of receiving that treatment. Okay? So CRD is only appropriate for experiment with homogeneous experimental units, such as laboratory experiment, where other effects are relatively easy to control. So, but CRD also can be used for non-laboratory experiment, as long as you can control the other effects. No? But most of the time, they are commonly used for laboratory experiment because it is easy to control the other effects. Okay? So this is a sample layout. Let's say that you have a treatment. T is for the treatment and R is for replication. See, let's say you have 3 treatment. Then you replicated it twice. Then you have this experimental unit here, class 1, 2, 3, 4, 5, and 6. Since then you randomly selected, since again, as I mentioned, that each experimental unit 1, 2, 3, 4, 5 has an equal chance of receiving this treatment. So we have 3 treatments here, then multiply by 2, so you have 6 experimental treatment experimental unit. So 1, 2, and 3, let's say this sequence number of drone is just one way of randomization. So let's say that you assign numbers for every treatment, then you select one, so you select you randomly pick that, then each of the experimental unit will receive equally the chance of having this treatment. So for experimental 1, 2, 3, and 4, this is the sequence. So let's say that experimental unit 1 received the treatment T2, the experimental unit 2 receive again the T2, the experimental unit 3 receive the T1, 4, T3, 5, and so on. So they have, so wala dili magmatter if T2 and T3 is T2 and T2 is nagtapad. So wala dili nato siya i-consider ng blocking niya this time. So all the experimental unit has the chance to receive the every treatment. Okay, so what is the advantage of this completely randomized design? So first is simplest analysis, then maximum degree of freedom among all design, then can follow an equal number of replication without losing efficiency. So I think this is the most important advantage of completely randomized design, or the CRD, that it can allow an equal number of replication without losing efficiency. But for this discussion, I will only focus on having analysis of variance for equal number of replication. So this gipa-emphasize aning can allow an equal number of replication without losing efficiency is that when you're doing an experiment class, there are some cases nga na atay mga missing data. Let's say for experimental katong ganina, there are 1 2 3 4 5 there are 6. There are 6 nga experimental units. So there are some cases nga let's say that the numbers the experimental unit number 6 wala kay nakuha nga data. Okay? So kung wala kay nakuha nga data diha, you can always you can analyze you can interpret the data gihapon bisan pag nawala ang kuan. So that's the advantage of having a CRD for your experiment. Then disadvantage requires a large number of homogeneous experimental units. So dapat katong 1 to 6 ganina, dapat equal gito sila. The same sila property o kung sa manada kung sa yuta pa siya, dapat equal sila kung soil texture o sa bada. Then usually applicable under controlled condition only. That's why it's really kuan lang no. Ang CRD is commonly used po siya for laboratory experiment. So there are two variation of kuan. So for analysis of variance, so this is importance. This is the highlight of the experimental design, the analysis of variance or the ANOVA. So this is the ANOVA for CRD. So there are two sources of variation. First is the treatment, since unsay treatment variation. So we need to find the difference between each treatment. Kung sabay ko anda, na ba siya effect karon. Then the second one is the experimental variation or the experimental error. Okay. So to discuss the design procedure for the CRD, let me have this example. Let's say that you have 7 treatment. You have a different fertilizer. Then you want to study the effect of this fertilizer, every fertilizer, to the yield or to the grain yield to your plant. Okay, so you have fertilizer 1 here. You have fertilizer 1, then mo na siya ang corresponding grain yield niya in kilogram per hectare. So you have fertilizer 1 up to the control. Okay. So step 1 is the first thing to do is to group the data by treatment and calculate the treatment totals and the grand total. Okay, for treatment total we denote this as T, and for the grand total we denote this as J. Okay? So in grouping it looks like this. Okay, this is your fertilizer 1 2 3 4 5 6 and your control. So first thing to do is to calculate the treatment total. So here is the treatment total. You just add this kaning ako ni class, i-add lang ni 2,537 up to 1,797. So you have this 8,507. Do this in all row. Okay, you have this, then just add this part here, then you can have this treatment grand total. Okay, so this is the grand total. You need to calculate also for treatment mean in order to calculate the grand mean. So treatment mean is just this value here, 8,507, divided by 4. There are 4 observed data for this one. So you have 2 1 2 7, then add this, divide by, there are 7, so you have 2,040. Okay, so that is the grand mean. So the grand mean means the average green yield for all this data here. So after that, you already calculate the grand mean, the grand total, this grand total here, then you also then you also have the total treatment for every fertilizer. So after that, you construct an outline for the analysis of variance. So the table looks like this. You have first the source of variation, which is again there are 2 for CRD. You have the treatment and the experimental error, then plus the total. Okay, the next column is the degree of freedom. Next one is the sum of square, the mean square, the computed F, then the tabular F for 5% and 1%. So we need to fill in the important data para ma-analyze na to karon kung unsa ang effect sa treatment karon dito sa grain yield. Okay. So first is the degree of freedom. So determine the degree of freedom for each source of variation. So to calculate, natin mga formula, established formula. To calculate the total degree of freedom, you have this formula that RT minus 1. R is the replication, T is the number of treatment. So just calculate that. R, sa base atong example, there are 4 replication. If we will look back, there are 1, 2, 3, and 4. Then we have 7 treatment, 6 fertilizer, and 1 control. So you have a degree of freedom of 27. Then for treatment, it is just T minus 1, which is the treatment, the number of treatment minus 1. So there are 7. So you have 6 degree of freedom for the treatment. Then for error, you can calculate by using this formula, T times the quantity of R minus 1. Or you just use total DF, the total is 27, minus the treatment DF, which is 6. So 27 minus 6 is 21. So the same with this formula. Okay, so after that, nanatay degree of freedom, let's proceed to the sum of square. Okay, so we need to calculate the sum of square. So before we before we calculate the sum of square, let's first calculate the correction factor. The formula for the correction factor is G squared, which is G is the grand total here, the grand total, which is 57, the grand total divided by N. N is the total number of treatment, okay, including the replication. So N is just R times T. Then treatment SS is just equal to the summation, the squared, the correcting sum of square of treatment over R minus the correction factor. Okay, why gi-minus niya siya sa correction factor in order to correct, since correction factor siya, in order to correct that para ang atong experimental unit is measured from the mean of our experiment. So sa iyang mean, no, para ma-measure siya sa variance day. Ang variance sa imong ang variance is measured from the mean of your treatment. Then total SS, sum of square, just the sum of the squared of all treatment, all observed variables, kanitanan dere, kanay 1, 2, 3 kanitanan, divided by, minus the correction factor. Then error SS is just equal to total SS minus the treatment SS. Okay, so using sa atong data nga na-gather, let's solve that. For correction factor, we know that we already calculated the G, which is the grand total, the 57,110, and is just equal to R times T. R is the number of replication, T is the number of treatment. Then you have this correction factor of 116,484,004. Okay, then for total SS, we have this formula. Follow this formula, that it is just the sum of the squared of every experimental unit. Okay, so you have kani sa isahon na ni siya class, i-squared ni tanan kani tanan dire, i-squared ni siya, isum, i-add dayon, then minusan din mo siya sa correction factor kani, which is CF. Then nakay total SS nga 7,577,412. So we have the total SS. The next thing to do is to calculate the treatment SS. So for treatment SS, this is just the sum of the squared of your treatment. The sum of the squared of treatment, balik ta sa table, mo ni ang atong treatment total. We have for fertilizer 1, fertilizer 2, fertilizer 3, 4, 5, 6, and control. So just i-squared lang ni sila tanan, then i-add, squared siya, then i-add, divided by the R, the number of replication, minus the correction factor, then you have a treatment SS of 5,587,164. Again, gi-minusan siya correction factor in order that the variance of the treatment must be measured sa mean. Okay? So, for error SS, total SS minus the treatment SS. So, just katong data nga lang na solve nimo minus. Then, you have an error SS of 1,990,238. Okay, so after calculating the sum of square, the next thing to do is to calculate the mean square. Mean square is just for there are two, since there are two variations sa CRD, which is the treatment and the error. So there are 2 MS lang po nga atong i-calculate. So for treatment MS is just treatment SS over T minus 1, which is T minus 1 is just the degree of freedom. Right? So plug and play lang. Plug lang kadra. So 931,196. Then for error SS, MS, the same, error SS divided by its degree of freedom, which is equal then you have this 94,773. So you have the SS, you already have the MS, then we can calculate now the F value. So calculate the F value for testing of significance. So in order to test if there's a significant difference between each treatment, we need to calculate the F. The same sa katong gibuhat sa mga previous nato nga mga topic. So calculate the F value. So F value for this is just the treatment MS divided by the error MS. So just plug and play, you have a F value of 9.83. Now this is the computed F value. So we need to compare this to the tabulated F value in order for us to solve, in order for us to interpret if there's a significant difference between each treatment. Okay, so to compare again the degree of freedom, this is used to in order for us to locate the required values dito sa atong F table. So degree of freedom for treatment, DF1 is for treatment, DF2 is for error. So all the time gid siya class, DF2 is always the error. So we have 6 and 21. So this is a table. Dili kay siya di kay maklaro, but you can look for this sa sa inyong F table to clarify lang ninyo. This is the 6 DF1, then this is the DF2 21, just cross that, then you have actually di po na ako maklaro, 2.572 ata. Okay, to 2.57. Okay, so based sa katong sa graph, the same sa process sa 1%, 6 and 21 gihapon ang gamiton. So for at 5%, so you have 2.57, then at 1% you have 3.81. Now after this, kung na kay value for this kanang gikan sa kanang table, we need to fill in the table katong atong gi-create kanina. So for treatment, you have this degree of freedom, 6, 21, then the total of 27. Just plug in the sum of square here. Then you can also calculate that this kaning value sa sum of square divide by kani mo ni siya 931.196. Then kaning value dere divide by 21, you have this. Then 931 divided by 94, you have this 9.83. Okay, now let's compare this to the tabulated F value. Since this computed F is significant with, it is greater than with the tabulated, we can say that at 5% and 1%. Therefore, we can say that our treatment is, there's a sufficient evidence that there's a significant difference between each treatment. So kibali lahi-lahi gid siya, na siya lahi-lahi gid nga effect. dito sa imong yield since it's greater than. So if it's highly significant, you put 2 asterisks if it is significant with 1%. But if the value is less than with 1% but greater than 5%, you write 1 asterisk lang in order to signify that it is significant different from 5% level. Then if it is less than for both 5 and 1%, then you put an S, which means that it is not significant. So therefore, we can say that there is no significant difference between each treatment. Now, we know that, okay sir, we know that there's a significant difference between each treatment used. So katong tanan nga fertilizer na agid sila kalahian. Now the question is, asa dito sa mga fertilizer karon ang naglahi? Asa dito? Dili man pud dito inyong tanan nga naglahi ito sila tanan. So we need to conduct another test for that. So that is post hoc analysis, but we will not include that post hoc analysis because it will take a lot of time to do post hoc. So but there are softwares nga like Species nga after nimo magamit ang makakandak og kani, they also analyze post hoc analysis. So ma-determine nimo which of those treatment ang significantly different with each other. So note that NS result means, for example, no, na NS yan na not significant. Note that NS result means that the F-test for analysis of variance fails to detect the difference between treatments. So it dili siya pasabot nga failure in experiment. But your experimental design or your analysis of variance fails to detect the difference. Maybe the difference is very gamay kay siya nga mo nang dili siya ma-detect sa imong analysis of variance, but it doesn't mean nga na fail ka. So maybe you can check your experiment and try to find what is wrong with kuan. Maybe if you increase the replication number in order para makita gid nimo ang difference between between treatments, or just like that, increase the replication. So after that, we will compute the grand mean, although grand mean is already calculated now. Grand mean, so grand mean and the coefficient of variation. So grand mean is kanina na-calculate na madaan sa table na to, which is 2040, but you can use this formula. Then CV, which is the coefficient of variation, it is measured in terms of error. So the greater the CV, the bad the model. Okay, na siya kakuan. So dapat gamay gid ang CV, which is the coefficient of variation, because it is measured from the error. So for this, just use this formula, 15%. So some of the they're using this ginabutang din lang CV. There is a bottom part, CV, and there kaning high. 2 asterisk means highly significant. Okay, so step 9. Okay, katong CV indicates that the degree of precision with which the treatment are compared, and it is good index to the reliability of the experiment. It expresses the experimental error as percentage of the mean. Thus, the higher the CV value, the lower is the reliability of the experiment. So man nga, the mas may kung gamay atong CV. Okay, so I think that's it for CRD, for completely randomized design. So next video, we will discuss the completely randomized block design, which is also part of the complete block design. So that's it. Thank you and goodbye.